So oftentimes when there's non-response in surveys, people just ignore it, hope for the best. That's probably the most common thing that people do. Now, that's valid if you think that the people who respond are the same as the people who don't respond and they're just random response rates. But if you're worried about whether the people who respond are different than the people who don't respond, then you need to start thinking a little harder. So in the Oregon experiment, one thing that people can do is take values of variables for the non-responders and compare them to the values of variables for responders. Okay? If there's truly random response, if people randomly decide to respond or not, then the values of these variables on average should be the same. The responders should have the same average variable as the non-responders. Okay? Just like for the same reason that when you randomly assign people to treatment and control, the average values of their variables across the two groups should be the same. There should be balance. So that's one possibility. But of course, the problem with that is you need the average values of variables for non-responders. But where do you get that from? Because they're non-responders. They didn't respond. Well, in some cases, if people have a complex survey, there may be multiple stages of the survey, and you may have people who respond early on and then stop responding later on. So you can compare values for the first stage with the responders and the non-responders, but you can't compare them at some point because at some point people stop responding. Okay? So that's one thing you can do if you have some data on non-responders. If you don't have data on non-responders, then one thing you're left to do is say, well, okay, I know that I'm not going to be able to learn anything about non-responders. Let's just see if we can learn something about treatment effects for people who respond. Okay. Now the problem is, in experiments, are the people who respond in the treatment group the same as people who respond in the control group? Okay. That is the bias, the non-response bias, balanced across the two groups? So that's something you can check in your data, and that's what they did here in the Oregon experiment. So here's table S7 from the appendix to this paper. In the panel A, they just have data on response rates. Okay? So up here we say how many people responded to the survey. Well, in the control group, it was 73%. And in the treatment group, there's some other number, but what they've presented here in this column is the difference between the average value in the control group and the average value in the treatment group. Lottery winners. Those are the treatment group. So the difference in those two means, 73 minus whatever the mean in the lottery winning group is 0.28. Okay? So basically it's 73% in both groups. So there's no difference in response rates. So that's one variable that we see that's common across the two groups. Okay? Now, down here in panel B, they have a lot of variables: age, female, black, other race, Hispanic, so some race ages, English as preferred language, address as PO box, etc., etc. Okay? And again, they have the average value of these variables in the control group listed here. And over here, the difference between this number and the average value in the lottery winners. Okay? So in the control group, the average age was 40 years, or 41 years. And in the treatment group, the difference between this and the average age in the treatment group was 0.2. So again, the average age looks basically the same. Okay? And so what they're going to do is compare all of these variables in the control group with the treatment group and see if they look the same. So if you do that comparison, you get these numbers here. And we see that basically it looks the same for age. Okay? The difference is 0.2, which is very minor, okay, in terms of age differences. A big difference would be, say, average age is 40 in the treatment group, and average age is 10 in the treatment group. This is the control group, sorry. That would be a big difference, okay? And that would be a sign that the people who responded in the control group were different than the people who responded in the treatment group because their ages are different, okay? But since we see that they're not different, we have a little bit of confidence that these two groups are similar, and for whatever reason people are not responding to the survey, it's the same across both groups. Okay? So now I'm going to talk about some of the other numbers on this table. So here, these numbers here are what are called the point estimates. Those are just the averages you compute. You get your data, you add up everybody's age, and you divide by the number of people. This number here in the parentheses is called the standard error. Okay, and it's a measure, if you remember from our earlier modules, of the variation in age. Okay, so it just tells us, sort of what are the largest number, oldest people in our group, what are the smallest, and sort of what's the distribution of that. So it's just a way of summarizing the data and telling us how much variation there is. And they give that for every single one of these. Over here, in parentheses, we get something that's called a 95% confidence interval. And again, that's a way of measuring how much uncertainty there is in these numbers. Okay? So here the 95% interval is minus 0.28 to 0.69. Now remember, the way you want to interpret these intervals is basically two things. If they include 0, then we say that there's no if we include 0, and the interval is very, very tiny, then we say that there's no difference between the control group and the treatment group in their age. If they contain 0 and they're very big, suppose it was minus 40 to positive 40. That's pretty big compared to age, So if that's the case, then you say that we just have an imprecise estimate. We don't have enough data to figure out what the true difference is. Here, it's what's called a precisely estimated 0, because 0 is in the interval, and the interval is very tiny, okay? And what I mean by tiny, that has to be relative to whatever your variable is. So is a difference in age of 40 to 50 big, or is that tiny? Well, that's sort of a subjective judgment call. I would say that's pretty big. Here is a difference of age in 0.2 big or small, or 0.28 or 0.69. That's pretty small. But again, it's a little subjective. So that's the way to interpret these intervals. If they contain 0 and they're very tiny, then you say there's no difference. If they don't contain 0 and they're very tiny, then you say there is a difference. Okay? And here, fortunately for the authors, all of these intervals contain 0, and all of them are quite small. Well, not all of them, but most of them are quite small, so they're precisely estimated. So from this data, the authors are going to conclude that whatever the non-response bias is, it's balanced across the two groups, and therefore we can learn the average treatment effect of having Medicaid for the people who responded. Okay? We would not be able to conclude that if we found that these numbers were very big, and therefore there was a big difference in these variables between the two groups. Okay. By the way, here's a good example of an imprecisely estimated number. Actually, no, I'm wrong. This is where you got to be careful. You got to remember the scale. So here is median income. So income, this is dollars, $44,000. And so these numbers, this is dollars, $400 to minus 400 to about positive 400. So that's actually a pretty small number relative to overall dollars. So if you don't look at what kind of variable it is, you might think, oh, compare it. Look, 400 to 0.3. Wow, this must be imprecise. But actually, it is pretty precise given the scale of this number here. So that's one way you can check for deal with non-response bias. But again, unless you assume that the responders are the same as the non-responders, you're only going to be able to get the average treatment effect for the responders.